Good morning, guys. Remember, I'm the basic guy, which, I mean, puts me a bit in a tight spot because you may have noticed yesterday our school collectively leapfrogged to the advanced level. At least, I mean, if that was basic yesterday, I don't want to know what will be advanced by Friday. Yeah, to cut it short, I want to call a vote. So what is going to happen is today I will just continue very slowly discussing symmetries and progress from symmetries towards topology. But then, I mean, the material I originally prepared, I mean, if I proceed as planned, it will involve a lot of repetition because much of what I'm going to tell has been implicitly or explicitly used yesterday already by the other lecturers. So plan A is I continue, I mean, as originally planned. That will involve repetition, will be boring certainly to some of you, but if others may feel they have some problem with following yesterday, I mean, maybe it's helpful to hear things twice. I mean, Dirac Hamiltonian approach to quantum anomalous Hall effect, stuff like that. The other option is I drop that. I trust that sort of it will sink in anyway. And I give you an introduction to the physics of static disorder in topological quantum matter. That promise will also be basic. I mean, it's not good, but it will be just different. So, who wants to follow route 1? And route 2? Oh, it's almost a draw. In which case I can decide, right? Or shall we? So, I mean, the disorder stuff you don't hear that often, so shall we go for that? I mean, Dirac Hamiltonians, you will see. Right. Okay. Now, okay, so let's now begin. Now comes another vote. I give you a Hamiltonian, I ask a question, and I want to answer, I mean, you to answer it quickly and, if necessary, instinctively, but give an answer. Yeah? So here's a Hamiltonian. H equals delta dagger, and delta is minus delta transpose. So you have a superconductor Hamiltonian without any further structure. I mean, spin triplet superconductor. What symmetries? Charge conjugation symmetric? Yes or no? Who's for yes? Please don't be shy. I mean, and hands up, I don't see anything. Okay, particle hole symmetric. No? Also some. No symmetry at all. Nobody. Okay? So let's investigate. Yeah? According to what I introduced last time, this guy, where are my notes? This guy is charge conjugation symmetric. And that follows from the following. Just let me find my right page. Yes. So you can define the matrix tau x acting in number space, and then you realize that H equals minus tau x H transpose tau x, and that is an anti-unitary operation, the transpose here, which reproduces the Hamiltonian up to a minus sign. So according to the table, this is actually C plus 1, because this operation squares to 1. Yeah? So C plus 1 charge conjugation symmetric. But now, I want to argue a little differently, and I write this guy in a second quantized representation. Yeah? So let's write it like this. And I discriminate between the first and second quantized by a caret. Yeah? But they are the same, of course. Free fermions. So I can write it like this: A HB CB plus C dagger A delta AB C dagger B plus Hermitian conjugate. Okay? Agree? And if we write it like this, I would argue this is the most dumb-ass Hamiltonian you can write down. It's totally stupid. It is structureless here, and it doesn't even know about particle number conservation. So it doesn't have any symmetries. Yeah, agree? That's a valid point of view. So what I want to advocate is that indeed this Hamiltonian in the first quantized representation looks as if it had some charge conjugation symmetry, and it has physical consequence. I mean, Majoranas, for example, rely on that. But from a fundamental perspective, this has really, it's a Hamiltonian which is totally symmetry-less. And it is, I mean, to avoid the confusion I alluded to last time, it is really, it is well to know these two levels of description. So let me now introduce to you time reversal and charge conjugation again, but this time in a what I would call physical, namely second quantized setting. And we can then discuss how first and second quantized levels interrelate to each other. And I mean, there is no one-line answer to or summary of what is going on, but it's good to know these two levels. Yeah? So, quick excursion into symmetries in a second quantized representation. That's what you find in most particle physics textbooks. Unfortunately, particle physicists only know Dirac and Young-Mills theories. I mean, they only talk about these, so they will always specialize at line 1 to Dirac particles. And but you can discuss all this in a more general setting, which, however, maybe some of you know, I don't know any good reference whether it is to be found. But anyway, I mean, the thing is that we have two fundamental symmetries in this setting, which is relevant for us. First of all, there's time reversal. And let me denote this by this fancy T. And we asked now how it acts on a second quantized operator. And it acts in the following way. It acts in the adjoint. I mean, you have this is our another way of actually writing the time reversal operator, which acts now as follows. It does, in general, involve an anti-unitary matrix. In most cases, this will be the unit matrix or Pauli matrix, sigma 2. Excuse me, unitary, yeah, some unitary matrix. And then you get here CB. So it looks as almost, this would just reproduce the second quantized operator up to unity, but this is anti-unitary acting. So which means that whenever you have a combination like this, you are supposed to complex conjugate. Yeah? That's time reversal. And there is a natural partner action on the creators, which is CB. Just has here the complex conjugate of this matrix elements. Okay, now there is particle hole symmetry. Particle hole or charge conjugation. These two are termed synonymously. So this guy here reverses time. That's where we need this from. The job of charge conjugation is to invert all quantum numbers. All quantum numbers get inverted, and it goes like this. C. And what does C do? It also involves a unitary, which this time I write as UC, a different one possibly. And by convention, I put here a complex conjugation, just matter of convenience, AB. And then it transforms our annihilator into a creator, and unitary. So there is C inverse is C. Some people claim, and I don't know where it comes from, that it should act anti-unitarily in the literature. But I mean, this will time will answer. But I mean, and this shows that there is confusion around. I mean, in the forums you see lots of discussions of this, but most people will agree it's unitary operation. Yep.
So this is particle the same as charge conjugation?
Yeah, I think so. Yeah, just. Mm-hmm. I mean, maybe this is more general, and it changes charge in particular, but it also changes other quantum numbers. All right. Now we can also then write down C and A, and this is by convention C, B, C, B. And so these are our symmetries. And now we call an Hamiltonian is C or T symmetric if if CH C inverse or TH T inverse equals H, and no minus here. Yeah, so this is really a proper symmetry, either unitarily or anti-unitarily implemented, but there is no minus signs of any kind. Now, it is, I mean, yeah, let me write this, let me write it in the perhaps more interesting case of C, what this means, yeah? I mean, we can ask now, what does this symmetry imply for the first quantized guy that is sitting in the middle? So let's do this as an exercise or example. So I write down something like that, CB, yeah? And act on it with C inverse. And now, well, I can write this as C, CA, dagger, C inverse, H, A, B. And this is a number here. C, C, B, C inverse. So here's the number. Notice that in the time, if I did this exercise for time reversal, I would get this number here, complex conjugate, yeah, because of this anti-unitary nature. But now it's just this number. And now you see how it goes. I mean, we plug in these definitions. And then this gets essentially replaced by CB, yeah? Oh, it's a matter of convention. And it's much more physical. Hamiltonian is particle-hole symmetric if you particle-hole exchange the creators and you get the same answer. I'll give you an example in a second. So we have this here, and now if we substitute this, we get here essentially a dagger. And then we bring it up front because we want to get back to the original representation, and that gives us a minus sign. So it comes from Fermi statistics. So if you plug it in, you will find that this is minus CD dagger, then U charge conjugation inverse H U C. With the transpose I also need because I swap orders. D C C plus a constant, and this constant vanishes for traceless Hamiltonians. The constant comes from Fermi statistics. If A equals B, I get something. So you see that our Hamiltonian gets reproduced if the first quantized guy equals that one times a minus. And that's our the way I introduce these symmetries. Okay? With time reversal, it's the same story, except that there would be no minus sign here. So that all looks pretty compatible. We have seen that the physical symmetries imply these combinations we discussed the other day. But there is a catch. And the catch is as follows. So are you with me so far to this point? The catch is, let's now go back to our example, which I wrote earlier, this totally structureless, non-particle number conserving Hamiltonian. You will not find a meaningful operation of this kind acting on the Nambu. You can try, but I mean, it's a good exercise actually to try to prove me wrong here. So you can try to find an operation of this type, anyone, which gives you a meaningful relation of this type. Oh gosh, that was painful. In that particular case, yeah, it just doesn't exist. So that Hamiltonian is formally, on the first quantized level, it has a formal, you can write down a formal relation. I would call it formal. Other people use different names. I mean, a constraint relation or what, but it's not a physical particle-hole symmetry. Now let me give you an example of one that is actually physically particle-hole symmetric, and then you can see what the essence of particle-hole symmetry really is physically, what it means, and probably many of you know this anyway. So here's one. It's actually one of our friends, because these days we always deal with linear dispersions. sitting on top of a filled Fermi-C vacuum. And if you have a linear dispersion like this, then we know that it costs as much energy to bring a particle at some positive momentum up here as it costs of kicking a hole or creating a hole in the vacuum down here, yeah? They cost the same energy, so there should be some kind of energy balance symmetry relation. And indeed, you can now define C as follows, namely Cp goes to C dagger, that is the dagger. And now comes the unitary operation, which I define as a unitary, I just define as a shift or exchange in momentum. So that can be unitarily represented, this P goes to minus P. And if you write down H equals C dagger P, P, Cp, sum over P, maybe some velocity here, then it's easy to check that this guy is particle hole symmetric under this operation. So you get the spirit, right? I mean, there is really something, some non-trivial in the energy balance going on here, while our superconductor Hamiltonian didn't have any of this. Okay? So it happens actually often that you have a kind of a symmetry which looks like a physical one, but is just comes from somewhere else. I mean, let me give you another example, which is also popular in this business we are doing here. I mentioned it before. This is a different example. I mean, take a Hamiltonian, Dirac Hamiltonian, in the presence of some diagonal potential that can be disordered or not. So you write here V, and here Px plus IPy, Px minus IPy. And then you realize that H equals sigma y, H transpose sigma y. And that is the defining relation for time reversal, usually in spin 1/2 systems. Yeah, so this is so class A2, but there is no spin here. These can be spinless particles. In this context here, you would need spin 1/2 to get this symmetry. Okay. So, yeah, that was this one remark. Now let me move slowly from symmetries towards topology, connect to topology, and I will then stop at that level because from there on, other lecturers take over or have taken over. So we had these. That's it. We had the other day we had these 10 different possibilities, which I have just listed here. So there's time reversal 1, 1, 1, 1, minus 1, minus 1, minus 1, and then 4 zeros. And because we had this doubling in the 0, 0 scenario, the same here with charge conjugation, and then the ensuing chiral symmetry, which is, say, here positive, positive, or present. I should present or absent. You don't discriminate between S plus 1 and minus 1. 1, 1, 1, 1. And here you can have a 1 or a minus 1. And so these are our 10 options, and they are labeled by these labels which we saw many times already yesterday, and I'll explain in a second where they come from, if you don't know yet. Now, what can we say in the most general terms about, I mean, really broad, I mean, Eagle's eye perspective? First of all, let me make, I mean, a remark where applications are concerned. Non-trivial symmetries. By non-trivial, we mean, so the trivial guys are this guy, that guy, and where are you here? This one. So involving time reversal, but no charge conjugation. And they were present and known in the pre-90s, mid-90s time. The others came later. And the other symmetries play a role in contexts where we talk about superconducting material mostly. I mean, so this, yes. I mean, these are the charge conjugation guys. And or in contexts where we have relativistic Fermi matter. When it gets relativistic, chiral symmetries usually pop up. Yeah? So you can let me call this chiral. You can draw an ever so broad distinction and say, if you have a guy that is charge conjugation symmetric but doesn't have a chiral symmetry, then chances are that it will play a role in superconductivity. But yeah, then there are others. I mean, like this one typically appears A3 is chiral. Is a famous, Dirac Fermion and random gauge potential. That's typical chiral application. But then there are also cases where you have both, like this. So BD1 is charge conjugation and chiral. And that means that it appears in both contexts. We know it as the Kitaev chain, and in particle physics, it's known as the chiral GOE, which plays a role in lattice gauge theory. And it also in superconducting context where you have chirality, it appears. So you have this kind of on the ever so broad double these application spectra. Now, what else can we say in ultra general terms about the non-standard symmetries? The thing is that systems with C equals plus minus 1 and or S equals 1 have quantum spectra, single particle quantum spectra that are symmetric around 0. Have spectra symmetric around 0. And the reason for that is as follows. I mean, you probably know it. Suppose I have an Eigen state. Yeah. Then my Hamiltonian anticommutes with my C operation. So I can hit then psi with C, however it's implemented. I mean, in this unitary matrix transposition and so on. And it will give me an Eigen state with negative energy, because the Hamiltonian anticommute. Yeah, and this, so you can cook up for each epsilon a state with different energy, and these states are then naturally linearly independent because they are eigenstates to different energies. There is one exception: zero energy. At zero energy, if you have a zero energy state, there is no telling whether this guy is actually a new state or whether it's the same state again. Yeah. So at zero energy, this mirror symmetry is lifted, and whenever you have a state such that it has zero energy and it reproduces itself under the symmetry operation, chances are that this is a topological zero mode. Yeah, I mean, it's so if you have a spectrum, no, let me draw it like this. It is here, it is symmetric around 0, but here you can have a zero mode setting, and once there is a zero mode here, you have probably heard this argument, then it's really nailed there. It cannot get away. There will no other state come which it can hybridize. It's just sitting there and locked. That's one way of motivating the topological stability. Clear so far? Questions? No? One last remark on this, and in one incarnation of the lecture notes I would actually expand on that, but I don't do it now. That is the following. In these systems, if you explore low energy physics, and that's what we usually do, right? I mean, say, take Majorana quantum wire, experimental situation, you hope there is a Majorana sitting there, but then there are these vicious Andreev bound states coming down, and you really want to know what's going on in this low energy sector here. And as a rule, what you should expect is both in disordered and non-disordered context is pronounced quantum interference phenomena going on here. So there's really, quantum mechanics is very important down here, and the reason is that whenever one guy wants to come down, there is a partner coming up. And the closer the more they try to get close to zero, the more they see each other. They correlate via the Hamiltonian. So very often you cannot get away with doing some first-order perturbation theory here. One really has to work a little more to understand what goes on in the low-energy sector. And there is a lot of discussion, say, in the context of Majorana Fermion bound states in quantum wires, what all this implies and whether it's actually Majorana or just two Andreev bound states and so on. They are seeing, yeah. So that is, and it's pervasive. I mean, in all symmetry classes, you have this. Life gets interesting close to zero, at zero energy. Up in the sky, somewhere here, they usually behave as if the symmetry wasn't there. That gives a zero energy point. Okay. So now that. Now I'm always pressing the wrong buttons. Yes. Now let me now move from symmetry slowly to topology and connect to what we had, what was already discussed yesterday in different ways. And what I want to do is I want to discuss now these symmetry classes first from a geometric perspective, and from geometry we can then move into topology. Yeah, so this geometric view is a gateway into topology, and that's also how things developed historically. And so, say, what do these symmetries, how can we relate between these classes and something geometric? And the clue is, I mean, it's a trivial remark, but it actually took some time to appreciate that this is a good idea. The idea is not to look at the Hamiltonian of a given symmetry class, but at its time evolution operator. Time evolution operator is an interesting guy here. So consider U IHT under the assumption that H belongs to one of these classes. No? So what can we say? I mean, say if T, C, S equals 0 in the totally trivial setting, H is just Hermitian. So H equals H dagger, and from that follows that U is in some UN. Remember, we were n-dimensional in Hilbert space, and that's all you can say. Now, I would like to suggest a view where, I mean, we mentally, we don't think about a given Hamiltonian, but about an ensemble of Hamiltonians, an ensemble which is such that in our n-dimensional space, it is irreducibly represented. So we think about all Hamiltonians at once, all symmetry allowed Hamiltonians, yeah, the whole lot of them. And then we create an ensemble, and if the space is really irreducible, this ensemble will fill up UN. Yeah? So we can say that the set of all time evolution operators sort of gives us a copy of UN. It sounds weird at first time, but it's a creative way of thinking about the situation. In particular, if you have a situation, I mean, some kind of like a maximum entropy setting where you have a Hamiltonian and there is junk going in, you think of a quantum device, and you wait for several milliseconds, then electronic degrees of freedom will have filled up fully the available Hilbert space. We call such a system ergodic. And such an ergodic ensemble then really defines a uniform measure on UN. So UN is full. Why is it useful? I'll tell you in a second. Okay, to appreciate where, I mean, why this is a good way of thinking, let's discuss another setting, namely TCS equals 1, 0, 0. So now we have time reversal dagger, this is a dagger, yeah? So now H equals H transpose equals H dagger. So we have a symmetry under transposition up to some stupid unitary matrix which can be conjugated away. In this case, we can ask the same question. I mean, suppose you have a time reversal invariant system and now you wait a long time, what will it fill? Which space? And the answer is, of course it's unitary. But what we want to get rid of are all anti-symmetric matrices. Anti-symmetric matrices are not tolerated. We only want to keep the symmetric guys, right? So what we have to do is we have to factor out the subgroup of UN that is generated by the antisymmetrics, and that's ON. So ON goes. And we arrive at this kind of coset space. Yeah? Okay. Now that you can do this for all 10 classes, and you will always, in each case, you either end up with a group case, group manifold, or a coset of two classical groups, some UN over SPN or something like that. So that's not very exciting by itself. But then, if we just fill this in here, like here a UN, and here, say, for the fun of it, I can never remember this, an SP 2N over a UN. I mean, you play these games. You notice that mathematicians have been there before. The thing is that the 10 spaces you get are called in mathematics, they are called symmetric spaces. I'll tell you in a second why they are called symmetric spaces. And this was all done by Cartan in the early 20th century. And the beauty of, there's lots of beauties about symmetric spaces, but they come in two families, compact and non-compact. These are compact spaces. They are relevant for fermionic quantum matter. Side remark, there is also bosonic non-compact versions which appear in the context of bosons. And there's only 10 of them. So you have just 10 symmetric spaces, 10 families of symmetric spaces. And they are labeled here. This is the Cartan notation, which draws connections for those who have a sweet spot for math between these spaces and the large families of classic Lie groups, which go by A, B, C, D names. That's why you have these funny labels here. And there are 10, and they are just parameterized by their rank. So this is the dimension of the symmetric space. But so 10 families of symmetric spaces of a given rank. And the realization then was that there is obviously a one-to-one relation between fermionic quantum symmetries and these symmetric spaces. And there's just 10 of them, and that's why we stubbornly, I mean, we can prove that you won't find any other fermionic symmetries. They always belong to one of these 10 groups. At this point, it's not so clear what you can buy for that knowledge, yeah? I mean, but actually, I mean, there's quite a lot. Let me briefly explain or discuss why they are called symmetric spaces. I mean, this is if you want, the algebraic way of introducing them. But there is a beautiful different way which connects between this ergodic maximum entropy approach and geometry. And very roughly, it goes like this: you take a symmetric space. You cannot visualize, but suppose you could, yeah. So here it is, a bit of symmetric space. And now you pick a point. It's just a side remark, but I like it. And these spaces are Riemannian. They have a scalar product. They're a scalar product. So that means you have you have differential geometry. In particular, you can talk about their curvature, and you can talk about parallel transport. So suppose you have here a certain curvature, yeah, and now you can parallel transport this through any point and go from here to here. So here you get, in general, a different curvature, right? If you have some weird manifold, it looks the same. But now it comes in a symmetric space. Every point, everyone, is symmetric under an isometry, under a flip of sign. I mean, under essentially the reversal of this geodesic. It's a symmetry point. That's a definition, a Wikipedia definition of symmetric spaces, and that has two consequences. It means that the curvature here equals the curvature there. So physically, geometrically, it means the guys look the same from all perspectives. You look at them, they always look the same. That's why they are called symmetric. In the physics context, these are our symmetries. Yeah, these are the discrete symmetries which flip you from, I mean, so that's why these symmetries imply a highly symmetric representation space under time evolution. Right. Now let me give you one concrete example where you can, so we can actually see this in a little more detail. What the symmetric space is and why it is so symmetric. So consider, yeah? Good. I guess you could, yes, why not? I mean, if you have a parameter and you, yeah. Yeah, I understand, but I would say that this is here a little bit more general. I mean, it applies even in cases where you don't have a natural connection, physically motivated connection. Yeah, so take a chaotic cavity. Well, no, so, no. But yes, I mean, so. In cases where Berry phase can be, this is surely related in some way, but yeah. Let me give you one example, and that goes as follows. Take our friend, the SSH chain, which we have seen yesterday so many times. So H equals in momentum space. No, we don't even need momentum space. We have here something, and here there's something there. Yeah. And the discriminating feature is that H and sigma 3 anti-commute. So that is your Carrel symmetry. Carrel symmetry. Now we ask ourselves what symmetric space does, and I take it back. Let's be 2 by 2. So think of this as a number, some Bloch number here. So if we go down to such a small subspace, well, it's just a number, then we can ask ourselves what space, in what space does the time evolution operator live? And the answer is, well, first of all, it's U2. I mean, U2 is clear, because this is the exponential of a two-dimensional Hermitian matrix, anti-Hermitian with the I. But then you want to get rid of the diagonal blocks. Yeah? And the diagonal blocks you can remove by removing everything that's generated by sigma 3 and sigma 0. And that means that you factor out a U1 and times a U1. So one U1 is here and the other one U1 is here. So that's our space. And it would appear here, you would see U2n over UN times UN. So this is the lowest dimensional representation of that. And what is the space? Just to check your geometry. No. Somebody must have seen this sometimes. Nobody? Okay, I give you a hint. Let's remove this one U and do it like this. SU2 over U1. SU2 over U1. No, SO3 is up to this double cover thing, which Andre mentioned yesterday is SO3 is SU2 almost. Spin. What does a spin do? Where does it live? On a Bloch sphere. This is a sphere. Yeah, you take, how do you see it? You take spin SU2, yeah, rotates everything. But now if you start from a symmetry broken state in a magnet, say, the guy is invariant under 1U1. So, so if you have a ferromagnetic substance, you have 1U1 that's going out, and the rest of SU2 gives you a sphere. So that's how one way of seeing that SU2 over U1 is a sphere. And the sphere arguably looks the same, but if you look at it from all perspectives. Yeah. In higher dimensional case, you would get the higher dimensional analogs of some spherish-like objects here. Yeah? Good. So that was that. So now we have basically all we need to know about symmetries and their geometric interpretation. And we can now move on from symmetries to topology and establish the link to what my colleague lecturers will discuss or have been discussing, oops, now I was not supposed to put, to dust this carpet here. Now I successfully did. Sorry. So if I had proceeded according to the plan, I would now introduce my two guinea pig examples of topological insulators, SSH chain and quantum anomalous Hall effect. But I guess you are all sick and tired of seeing them introduced, and we had them lots of times yesterday. But keep them in mind. There are these two guys, and very quickly, the SSH leads to a Hamiltonian, the chiral Hamiltonian of Now I'm really serious of this block structure. I again write it in a Bloch momentum representation, just for explicitness. And Zk is then typically T times e to the ik minus some mu, some complex number. And there is a quantum anomalous Hall effect Hamiltonian, which you can write as like this on a lattice. If you something like that, sigma x plus sine ky sigma y plus some r minus cosine kx minus cosine sigma 3, right? Now what can we say about these guys? This one is an A3 Hamiltonian, and this one here is A. It doesn't have any symmetries, besides hermeticity. And now we want to understand topology, and there are different ways of doing that. Yeah. One way that does not work is to stare at the band structure. Although Andre is now telling us about intelligent ways of making sense of band structures, but I think we can agree that if we look at the band structure of any of those guys, then we generically have a gap somewhere here. And here we have, say, n plus unoccupied bands, n minus occupied bands, and the totality of n plus n minus total bands. So just staring at this will not help. What does work, but is not the best way of going, is to do the following. You can think of it, this situation as follows. This data here, yeah, you can describe it as a map. So we have a map in general of some detours. Say there's a Brion zone underlying here. It's one-dimensional, two-dimensional, and so on, into a symmetric space, or something that is tangent to a symmetric space. Essentially, and some k goes to x, k, th, k, something like that. And now you can start exploring the topology of that map. What do you mean by topology of map? You have here something that's topologically non-trivial in some sense. Here you have something else. And topology usually establishes relation between different topological spaces via maps. Yeah? And it can happen that your map is such. If everybody goes to unity, then it's obviously trivial. But it can happen that your map is such that you have some, you can associate some invariance to it, some Brauer degree or whatever they have in topology. That works, but it's not the best way. The better way, there are several better ways. And let me just list three of them, essentially. Three ways which from a practice perspective, which I think are good for describing topology, and several have been in use already here. Number one is you don't look at the Hamiltonian, but it's Eigen States. Eigen States, yeah? So the Eigen States are, in a way, this is a better way of looking, because it not only tells you something about the totality, the Hamiltonian, but you also have to can communicate which eigenstates are occupied and which are not. So this is the essential extra information you will provide in this way. And it goes as follows. Information on eigenstates is encoded in what? And let me just bring this up for class A, the simplest case. I mean, this one here. You have for each k, you have a unitary matrix telling you which contains the eigenstates at given k, yeah? And it's n-dimensional. So it has the information about the eigenstates corresponding to these states here. This one, that one, with these eigenvalues. But then you can argue that you just don't care about any basis transformations in here, which just change the labeling here, and the same down here. What you're interested in is about the relation of how these relate to each other. So that means that you can get rid of this coset, of this factor group, which is smaller n plus n minus is n. And you naturally arrive at cosets of this type for all 10 classes. I mean, if you're living on a different symmetric space, different guys appear here and here, but it's always this structure. And they have a name, they are called Grassmannians. These are, this is the overarching name for these animals, these cosets built from classical groups, Grassmannians. And then, I mean, the homotopy approach to topology just replaces this symmetric space here by the equivalent, but no, somewhat richer information. You put here the Grassmannian. And now you explore the mapping from the torus into the Grassmannian space. Let me give you 2 examples. Tell you how this unfolds in these 2 cases here and here. What is a Grassmannian here? Here, this is a 2-band model, yeah. And you see, you diagonalize it. The diagonalizing vector is just the eigenvector of these guys here, and you have one for the upper and the lower band. So the lower band eigenvector just follows the orientations described by these, and that means that the Grassmannian is equivalent again to a sphere. This is the information about the occupied eigenstate, and it's U2 over U1. And our map then is a map from the 2-dimensional Brillouin zone, the 2 torus, into the sphere, and these maps are classified by integer winding numbers. So, so that's the, and I want to stress that this is the fundamental concept. The fundamental concept is homotopy. It's not Chern numbers or Berry curvature or all that. These are all languages to describe what's going on fundamentally. So fundamentally, if you have a non-trivial topological phase, you have a winding. As you go around the torus, you will fully cover the sphere. And this map from the torus to the sphere has a winding number 1. And now you ask yourself, how do I compute you? And then you do it by the pullback of the curvature form, and that's what we call Berry phase integral or Chern number and all these names that go with it. But these are second order concepts, yeah? And it's important to know because sometimes you really want to operate on the most fundamental level and not get caught up in calculations with complicated objects, yeah?
So this Grassmannian, does it depend only on the number of occupied versus n times, or would it be the same with different symmetry classes?
No, if you are, say, in a different symmetry class, you have to trade this guy here for the corresponding symmetric space, and that one here accordingly for smaller manifolds. Yeah. And the way, I mean, it will certainly appear sometimes during this lecture, during this week, there is this famous periodic table of topological insulators, symmetry classes versus physical dimensions, and what is going on topologically. You must have seen it. It shows up in every talk. And this is, the structure can be, or has been understood historically, first mathematically by Bott from representation theory reasoning, and then by Kitaev who just explored this homotopy structure systematically in terms of category theory, and then you can write down this table, yeah, on very fundamental grounds, without worrying about Hamiltonians in detail. Here, very quickly, the eigenstates essentially, let me just describe this. They can be written as 1, and then comes here essentially Z over Z modulus, something of that flavor. These are the eigenstates of this animal. And now you see the Grassmannian is this, which is a unit modular number, U1. So this is U1, so it's a circle. And what we are dealing then with is a map from the Fermion zone circle into that circle, and it has a winding number if and only if this is larger than mu. You know? So you can just see it. I'm just telling you in general ways what you have seen already. 5 to 10. Oh, well, that's luxury. I thought it was more. Okay, so yeah, I'm perfectly fine. That is this approach. And again, I mean, once we know what can go on homotopic grounds, we can worry how to actually compute it. And I don't want to get carried away here, but there are these different vehicles depending on which dimension and which symmetric space we are. So, for example, here you would characterize the homotopy degree by a Chern number, which you have then to compute for a concrete mapping. Here it would be a winding number, and then there are more complicated cases, especially if you have time reversal invariants around, where objects such as known as Chern parities sneak into the game. But conceptually, it's always like this. Yeah? So that was approach number 1. Very formal, very powerful, but sometimes not very rewarding if you look at one given system. The approach which all things taken into account, I think is, I mean, in practice, if you really have a system and you want to do something which often works best, is a Dirac-Fermion approach. So that's another way of getting these numbers under control, yeah. But now in a more flexible manner. And the situation here is as follows. I mean, schematically, you know that for a certain value of R, namely R equals 2, this guy switches between topological sectors, so from a winding to a non-winding map. And that can be said about pretty much any insulator, and we have seen examples already, and you then know that at this point there must be a gap closing point. You have a singularity. You linearize around the gap closing point to obtain a Dirac Hamiltonian. You get first order zeros, yeah? And say in the SSH context, you would have, say, a band structure, I don't know, like this, above and below the transition, but then right at criticality, you have this, and so you're dealing with a massive Dirac-Fermion here, one-dimensional, and you can ask yourself, can I get this number from this Dirac-Fermion approach? And the answer is it's a qualified yes. The thing is, if you compute I mean, Chern number like objects from a Dirac-Fermion approach, you typically get the numbers wrong, and that is because to get the full winding number or Chern number, you really have to integrate over the whole structure. So if you sit here, you typically get only 1/2 of this relevant number, but you don't care so much actually about the number, but you want to know how the number changes if you go from one topological sector to another one, say Dirac-Fermion with positive mass to negative mass here, yeah? And the jump, the change, integer change in the Chern number or winding number, that can be obtained from the Dirac-Fermion approach. That is why we like it so much, and can actually obtain all that's of interesting topology-wise from these guys. And there is another bonus. You often want to consider surfaces or something like that, where a topological index changes as a function of an external parameter, and you can just the same give these here some weak coordinate dependence, and then study in some semi-classical way what does my Dirac-Fermion do at a surface as a mass interpolates from plus to minus 1, play these games and so on. So according to plan A, in the lectures I would have told more about that, but we are seeing it lots of times now during this week, so I guess I can skip that. And then there is the third approach. One more thing. The Dirac-Fermion approach, we have also seen that yesterday. Titus explained that in a pretty advanced setting, an example of this. The Dirac-Fermion approach can also be very fruitful in exploring structures in this periodic table of insulators. What's going on? Let me just give you the idea. Say, I take a quantum anomalous Hall effect Hamiltonian, describe it by a Dirac-Fermion like this, and then what I can do is I can, this is a game known as dimensional reduction. I can just decide for the fun of it to wrap up my surface and to build a cylinder out of it, yeah? And in that case, one of the momenta will be frozen out if I go to low excitation energy. So I go from a generally massless fermion in 2D to a generally massive fermion in 1 dimension lower. And if you do this in this concrete setting here, you go from an A system in D2 to an A3 in D1. So if you go into it and write down here the Dirac Hamiltonian corresponding to a compactification like this, of that one, you go from here to here. And if you look into the periodic table, you have entries like A, A3, and no, let me do it. This is A3, A, and here you have dimensions 1 and 2, and you have structures like that. They always appear in these diagonal. You must see them. There's always this. And so that would be an example how by dimensional reduction you go from an A in Z2 to an A3 in same index, same one in, topological number in 1 dimension lower in different symmetry class. Yeah, so that's again a Dirac game, which one can do. Okay, so let me, this is all very superficial, yeah? Mm-hmm. The thing is, if you do this here, and you trade one of these guys by a constant, and then require that for low energies, this constant should be 0, because you don't want to pay this high excitation energy price, yeah? Then you basically keep this one, you kill that guy, and this becomes unity, and now you have a Hamiltonian which has only sigma x and sigma 3 in it, and therefore anticommute to sigma 2. And that's then a chiral one, yeah. Right, and last minute final remark, and that's what I will come back to. When is my next? Tomorrow? Tomorrow, okay. So next lecture. What do we do when we have impurities? If we have impurities around a disorder, all this goes bust. Yeah, you don't have any Fermion zone anymore. And you really have to start thinking again what to do. And the teaser answer, because that's what I want to explain tomorrow, is that in this case you really, you again have a map into some symmetric space, but you drop the torus side because it doesn't exist anymore. And instead you should work in a pure real space setting and replace this momentum by certain gauge fluxes, real space gauge fluxes, which you, and this then leads to this, you remember there was a talk by Jens where we had symmetric spaces, one column, the native symmetric space, and there was this other column on linear sigmas. So this is then the game, the approach to follow. Purely real space. But topology can, of course, not change. If you have a bit of dirt in a system, topologically it's still the same. So we just need a different approach. And that's then what I will talk about tomorrow. Okay, I stop here. Thanks.